few notes on tension as you get going on some of these problems here, in particular 4 things. First thing about tension here is tension is always pulls. Pulls away from its point of contact. So whenever a rope is attached to something, you never would imagine the rope is pushing on the object. There's some funny t-shirts and things and sayings you can find on the internet that basically says you can't push on a rope. And that is exactly what we're sort of saying here. So you can sort of imagine that here, that if you have an object like this, which is sitting on a flat surface like that, and you attach it to a rope, if you were going to stand over here and try to interact with the object somehow by doing something to this rope, you would never expect to push this way on the rope and expect anything to happen to the box. The rope would just sort of fall into the ground and everything would be over. You would always have to say, hold on to the rope nice and tightly right there and pull away from the rope with some force F that comes from your muscles or something to get it going. And if you pull away with force F, you can imagine that tension being transmitted through the rope here, and there'll be a T pulling away on that object like that. And so once again, here's the contact point of the tension, and notice it's always pulling away from the point of contact. So that's the first thing, is that whenever you draw ropes attached to objects, you always draw the tension pulling away from the object. So here could be a block here, and here could be a block here, and there could be a rope between them like that. There will be a tension pulling away like that, and this tension would be pulling away like that. This might be just as counterintuitive as you can think of here. You might think of, well, if the object is being pulled this way or something by the same person here on a different rope, shouldn't all the tensions be in the same direction? The answer is no. Tensions always pull away from the points of contact, so you really don't have a choice, though, that if the ropes are going to be connected by 2 blocks, this one's going to pull away towards the right, this one's going to pull away towards the left. Even though this block might be moving in that direction, the tension in the rope will still be pulling that way. It always works like that. Just as one more example like that, here's an Atwood machine. Here's a block here and here's a block here. If there's a tension, this is the same rope going around like that, there'll be an upwards pull like that and an upwards pull like that, always away from the points of contact. That's just always the way it works. You would never draw, say, an Atwood machine like this with a block right here and a block right here, and you would never draw the tension pointing down like that. You would never do this because that's not pulling away from the point of contact. So this is not a correct figure here. Tensions always pull away from the points of contact. That's point number 1. Okay, point number 2 about tensions. Here we go. Has to do with the signs. So the sign, and by the signs I mean positive and negative of T's are opposite on opposite ends of a rope. So the signs of T's are opposite on opposite ends of a rope. You have to get a sign convention in these problems because that has to do mathematically with how the sums are going to work out and eventually predicting how something's going to move. Here's an example here. Here's those 2 blocks again sitting on the table like this and like this. And here's that person pulling on it like that. So here's the person right here holding on to the end of the rope, and say the person's pulling this way with some force F. Now we like to call the right direction usually positive, and so we can go ahead and do that in this problem. We can call this a positive F because right's usually positive force. Now, what is also in this problem is that these 2 blocks are connected by their own rope, and as we saw in the last case here, we drew a tension this way because tensions always pull away from the points of contact, and a tension that way, pulling away from its point of contact. Now here you go. Signs of T's are opposite on opposite ends of the rope. Let's see what that means for us. If we call this direction positive right here, this is the same mass right here because the rope is directly attached to it. This force will generate, say, let's say the tension, the pulling tension over that way like that. You're just pulling on it. So that'll be to the right. So if the force is positive, this will be positive as well because that's all to the right. But now this tension points to the left. That's going to have a minus sign on it. And that just has to do with looking at this one block here, looking at this one block and going, okay, right is positive and left is negative. That's okay with us. But now what do I do with this tension? Well, signs of tension on opposite sides of the rope have opposite signs, so if this is a negative tension, this has to be a positive tension over here. That's just the way that's going to work out. Let me show you another example of the Atwood machine. That's a classic one where it's really easy to goof up the signs on that one here. So here's a mass here, and here's a mass here. Something like that. So here's an M1, and here's an M2. Something like that. So we can go ahead and draw the tensions on it like that. There'll be a T like this and a T like that. And notice I am not calling it T1 and T2 because it's the same rope going over the pulley. And so it's going to be the same tension in there. But now as far as the signs goes, well, this doesn't have anything to do with tensions, but I'll put them on there anyway just to sort of complete the story. M2 has a weight down in M2G like that, and M1 has a weight down in M1G like that. They both have their weights in there. Now, if they came in and started putting signs on these things, we like to say down is negative, so we'll put a minus sign right there. But if down is negative, up is going to be positive. That's just how the signs would work for this block, because down is negative, up is positive. But now what do we start doing on the other side? We're not so free to choose the signs anymore over here, because signs on opposite ends of the rope have opposites. Signs of the tensions on opposite ends of the rope have opposite signs. So if we go back here, this is a positive T, that has to be a negative T. But now we're in the case here where we look just at this block over here and we see, well, if negative T is up, the weight must be down over here. Positive M2G must be down on this side because up has to have an opposite side than down. So that's what the sign conventions sort of do for us like that. Opposite ends of rope always have opposite signs for the tension. And let's, I guess, look at one more example of that, just to make sure we sort of have that. And I guess we can look at a problem that looks something like this. There's another one that comes up from time to time. Here's a pulley, and here's a pulley here and here. There's a mass sitting here, and a hanging mass here, and a hanging mass here. Here's a rope going over these pulleys here. A couple of ropes like that. Two different ropes. Now, they are different ropes, so they will have different tensions, but let's just see if we can get the signs at least labeled on. The lesson that tensions always pull away from the points of contact. We can do that first. We can call that a T1. We can call that a T1. We can call this a T2. We can call this a T2. The reason why they're T1s and T2s is because they're different ropes. They can't have the same symbol. Now, what about the signs? Well, if I want to call up positive over here, that'll be a positive T2. But because the signs of tensions are opposite on opposite ends of the rope, the rule that we do at the very beginning, if this is a plus T2, that's going to be a minus T2. And now we look at this block. Apparently, right is negative. That means left has to be positive. But now we're in a new rope over here, so opposite tensions have opposite signs. If this is a plus T1, this can be a minus T1 right there. So we've labeled all the signs in there, and this doesn't have anything to do with tension, but just for the sake of completeness, let's just put the weights on there. This will have a weight here. Say if this is M1 right here, it's going to have an M1G down. What sign would M1G have? Well, if up is positive over here, it's going to have a minus sign down like that. And we can go over here and say if this is M2 right here, this is going to have a downwards M2G like that. But if up is negative, down has to be positive because that's the way the ups and downs work in this particular case here. And notice that by setting the sign convention like that, we have a nice consistent sign convention for the entire motion. It works like this. Suppose the system is moving like this. M1 moving down, M1 moving up, and this mass in the center, say, moving over that way. M1 down means this one's moving in the negative direction. If this one moves down, this one has to move up. That's its negative direction. And if this is moving down and this is moving up, this one has to be moving to the right. That's that one's negative direction. So see, the sign convention is nice and consistent throughout, and that we can conclude that if something's moving in a negative direction, this is moving down, this is moving up, and this is moving to the right. Likewise for the positive direction. If everything was moving in the positive direction, this one would be moving up, this one would be moving to the left, and that one would be moving down. So that's the way the sign conventions are going to work out on these things. But just keep in mind, whenever you label the tensions on these things, tensions on opposite ends of the rope must have opposite signs for a nice consistent sign convention.